In every process, there are common cause and special cause sources of variation. Common cause variation is deemed healthy to the process. Special cause variation is the type of variation we seek to identify and eliminate. Common cause variation leads to processes that are stable over time and predictable. Special cause variation is the source of instability. Processes can be unstable if either one or both of the process average or variation is out of control. When identifying special causes, a process control chart can show a lack of process stability through several types of patterns, including points outside control limits, trends, points on one side of the central line, cycles, and so forth. Assessing the normality assumption may be tested using the chi-squared hypothesis test. Observed results are compared to expected results, and the chi-square statistic is computed. This test will be explored in greater detail later. If we have continuous data, more robust tests can be deployed, including the Kolmogorov-Smirnov goodness of fit test, the Shapiro-Wilk test, or the Anderson-Darling test. Kolmogorov-Smirnov does have limitations compared to Shapiro-Wilk. With Kolmogorov-Smirnov, we must have continuous distributions, and the distribution must be fully specified. In other words, the mean and the standard deviation must be known. The Anderson-Darling test is a modification of the Kolmogorov-Smirnov test and gives more weight to the tails of the distribution. Many times we cannot claim normality of the distribution. This is not necessarily a bad thing. As long as we can establish that the shapes of the distributions are the same using a chi-square test, regardless of what the shape may be, we can successfully perform several useful inferences. Establishment of a normal behavior opens the door for using z-scores and finding probabilities. We use these probabilities to determine if we fall in certain ranges of the specification. The capability index, CP, is defined as the difference between the upper spec limit and the lower spec limit divided by 6 times the standard deviation. Note that CP assumes that the mean is centered and will remain centered. R bar and D2 are derived from the control chart parameters. In general, CP greater than 1.33 is capable. A CP between 1 and 1.33 is capable with tight control, and a CP less than 1 is considered incapable. Cpk accounts for processes that are not centered. Of the two calculations, we assign the smaller of the two as Cpk. There is a direct link between calculated Cpk and the z-score. Z-score is in units of standard deviation. It is the sigma level. We can also equate to parts per million defects. Note that Cpk of 0.33, we have a z of 1 and almost 700,000 defects for every 1 million opportunities. At Cpk of 2, this means that z is 6. This delivers 2 defects for every 1 million opportunities. Schmidt and Lonsby have offered a useful closed-form relationship between ppm and sigma level. While we have technology and tables to facilitate quick correlations between ppm and sigma level, this formula can still be useful. CPM is another capability index given by the formula shown here. CPM is similar to CPK, but bias from the target is directly taken into consideration. It is based on the Taguchi index, which places more emphasis on centering the target. The performance index is similar to the capability index. The calculation of standard deviation is now based on process performance. This is derived from the data. Like CPK, Ppk is a performance index that accounts for processes that are not centered. Of the two calculations, we assign the smaller of the two as Ppk. Processes are typically assessed based on one operator on one shift, with one piece of equipment and a homogeneous supply of materials. While this is not a realistic state, it will reveal a process state with a smaller degree of variation. As factors for time, multiple operators, various lots of material, environmental changes, and so forth are added, each of these contributes to increasing the process variation. For situations where data is limited in amount and scope, an individual's moving range chart or a modified X-bar R chart is recommended. This tool measures piece-to-piece variability. As we might expect, any capability results should be considered preliminary. As the number of data points increases, the calculated process capability will approach the true capability. Recognize that variable data is preferable to attribute data. Variable data, therefore, requires less data per group and a smaller number of groups over attribute data. As a general rule of thumb, one can expect a 1.5 sigma shift between short-term and long-term data. In other words, we expect the variation to increase and the capability to decrease over time.